In 1943, long before American tanks rolled through the streets of France, before German Panthers burned beside hedgerows in Normandy, and before Allied crews learned they could finally face the best armored vehicles in Europe with confidence, a shell slammed into a steel plate in upstate New York and failed. The impact lasted less than a blink.
If you want more content like this, subscribe now and comment below.
There was a sharp flash, a violent metallic crack, and then silence. When the dust cleared, the armor plate was scarred but intact. The projectile that was supposed to punch through it had shattered into jagged fragments scattered across the frozen ground. For the engineers standing behind the protective bunker, the result was deeply unsettling. If this happened in the laboratory under controlled conditions, what would happen when young American tank crews faced German armor in battle? What if they fired first and still lost? That question haunted the men at General Electric. They were not soldiers. Most wore white shirts, thick coats, and safety goggles instead of steel helmets. Their weapons were high-speed cameras, X-ray equipment, hardness testers, and notebooks filled with equations. But the work they began in 1943 would help solve one of the most dangerous problems of the Second World War. How do you break through Panzer armor that seems almost impossible to destroy? The answer was hidden inside steel itself. To understand how important this work became, you have to return to the battlefields of North Africa. On February 14, 1943, German forces under Field Marshal Erwin Rommel launched a powerful offensive against inexperienced American troops in Tunisia. During the Battle of Kasserine Pass, U.S. tank crews encountered German armor and anti-tank guns that were far more effective than expected. American commanders received a harsh lesson. It was not enough to build tanks quickly. Those tanks needed ammunition capable of defeating the best enemy armor in the world. At that time, many American armor-piercing shells worked well against lighter vehicles. But as German engineers introduced better tanks, especially the Panther and Tiger, the problem became much more serious. The Tiger I first appeared in combat in late 1942. Its frontal armor was thick and nearly vertical, while its famous 88 mm gun could destroy enemy tanks at long range. Then came the Panther tank, first used in large numbers during the Battle of Kursk in July 1943. The Panther introduced a new challenge. Its glacis plate was 80 millimeters thick and sharply sloped at 55 degrees. That slope made the armor dramatically more effective. A shell striking that plate did not face just 80 millimeters of steel. It had to defeat the equivalent of much more. Worse, the angle increased the chance that the shell would glance away or break apart. To frontline crews, it felt as if German armor had become almost invulnerable. The U.S. Army Ordnance Department understood the danger immediately. If American shells shattered on impact, crews inside Shermans would be forced to close to deadly ranges, where German guns held the advantage. The Army turned to some of the best industrial scientists in the United States. Among them were engineers and metallurgists at General Electric. GE was already a giant of American industry. Its laboratories in Schenectady, New York, had worked on turbines, X-ray systems, and advanced metallurgy for decades. The company had some of the finest experts in materials science in the country. Now they were asked to solve a battlefield problem measured in thousandths of a second. When an armor-piercing shell struck steel at nearly 3,000 feet per second, why did some penetrate while others shattered? The answer could save thousands of lives. The GE engineers began by treating the shell and armor as scientific specimens rather than military hardware. They collected fragments from failed tests. They examined cracks under microscopes. They measured hardness and grain structure. They used X-ray technology to look inside metal without cutting it apart. Every test produced more data. But the first results were troubling. Many American projectiles were extremely hard. That hardness helped them keep a sharp point and concentrate force. Yet excessive hardness also made them brittle. When a brittle shell struck tough, sloped armor, it could crack instantly. Instead of penetrating, it disintegrated. To the crew firing the round, the result looked like a harmless spark. Inside the laboratory, it looked like a catastrophic design flaw. The engineers realized that penetration was not simply a matter of bigger guns. It was a delicate balance of hardness, toughness, shape, and velocity. If the projectile was too soft, it deformed and flattened. If it was too hard, it shattered. If the nose shape was wrong, it ricocheted. If impact velocity was too high, the shell could destroy itself. This was not brute force, it was physics. One of the most important tools in the investigation was high-speed photography. Special cameras captured events too fast for the human eye. Frame by frame, engineers watched shells strike armor and break apart. The footage revealed something remarkable. Failure often began at the projectile's nose. The tip cracked first. Those cracks spread backward through the body of the shell. In a fraction of a millisecond, the entire projectile came apart. The shell was defeating itself before it had a chance to defeat the armor. This insight changed everything. The solution would not come from adding more explosive filler or simply increasing velocity. The shell had to survive the initial impact. That led engineers to refine the heat treatment process. Steel projectiles were heated to precise temperatures, quenched, and tempered. Small changes in timing and temperature produced major differences in toughness. A shell treated one way might shatter. The same shell treated slightly differently might stay intact and penetrate. The margin for error was astonishingly small. The engineers also studied captured German ammunition. German armor-piercing rounds often used carefully engineered caps and nose designs to improve performance against sloped armor. American scientists examined these features closely. One innovation proved especially valuable: the armor-piercing cap. This soft steel cap sat over the projectile's hardened nose. On impact, it absorbed some of the shock and helped prevent shatter. It also improved the shell's grip on angled armor, reducing ricochets. The concept was known, but GE and other American researchers helped refine the metallurgy and manufacturing needed to make it work reliably. Another outer cover, called a ballistic cap, improved aerodynamics and preserved velocity at longer range. Together, these features transformed shell performance. The most famous result was the 76 mm M62 APSI round used by American tanks armed with the 76 mm gun. Against the Panther's frontal glasses, no practical tank gun round of that caliber offered an easy solution. The slope and thickness were simply too formidable at common combat ranges. But the improved ammunition significantly increased effectiveness against the Panther's turret, side armor, and many other German vehicles. It also gave crews more confidence that a well-placed shot would work. Confidence mattered. By late 1943 and early 1944, the pressure on American engineers intensified. Operation Overlord was approaching. On June 6, 1944, Allied forces would land in Normandy. Thousands of tanks would soon be fighting in the hedgerows of France. Every improvement made in the laboratory had to be produced on a massive scale. Factories across the United States began turning out millions of rounds. Consistency became as important as innovation. A shell that worked perfectly in one test but varied in production could not be trusted in battle. GE's expertise in industrial quality control helped ensure that metallurgy remained uniform from batch to batch. The challenge was enormous. Each projectile had to be cast or forged, machined, heat-treated, fitted with caps, inspected, and loaded with explosive filler and tracer components. A defect invisible to the naked eye could mean failure at the worst possible moment. In Normandy, those moments came quickly. American tank crews entering the Bocage in June and July 1944 faced concealed anti-tank guns and German Panthers positioned in narrow fields of fire. The Panther's high-velocity 75 mm KWK 42 gun was deadly. At long range, it could penetrate the frontal armor of most American tanks. The Sherman's greatest strengths were reliability, mechanical simplicity, and numerical availability. But its crews knew they needed effective ammunition to survive encounters with German armor. By this stage of the war, improved armor-piercing capped rounds were reaching the front in growing numbers. Their impact was real. When shells struck side armor at favorable angles, they were far less likely to shatter. Penetration became more dependable. That dependability changed tactics. Tank commanders could engage with greater confidence rather than assuming their first rounds would fail. The science of metallurgy was now shaping combat decisions in the fields of France. On July 25, 1944, during Operation Cobra, Allied forces broke out from Normandy. American armored units advanced rapidly across France. As the front moved, reports flowed back to ordnance officers and engineers. Which rounds penetrated? Which failed? Which shattered? The feedback loop continued. The war itself became a giant testing ground. The engineering race did not stop in 1944. As more powerful weapons entered service, including the 90 mm gun mounted on the M26 Pershing, improved armor-piercing ammunition remained essential. The same principles GE engineers had helped clarify still applied. Keep the projectile intact. Balance hardness with toughness. Control the shape of impact. Defeat the armor before the armor defeats the shell. In December 1944, the German army launched its last major offensive in the Ardennes. The Battle of the Bulge threw American forces into some of the hardest fighting of the war. Snow covered the forests. Visibility was poor. German Panthers and Tigers once again led attacks through narrow roads and villages. But by now, American ordnance was far more effective than it had been in Tunisia. Tank destroyers, anti-tank guns, and armored units used ammunition built on lessons learned over 2 years of research and testing. Every successful penetration in the Ardennes was linked, in part, to work done far from the battlefield. Inside the steel, the secret had been cracked. The final months of the war brought American armored forces across the Rhine and deep into Germany. On March 7, 1945, U.S. troops captured the Ludendorff Bridge at Remagen, opening a path into the heart of the Reich. German armor still fought fiercely, but Allied industry and engineering now held a decisive advantage. The laboratories had delivered. What made this achievement remarkable was that there was no single dramatic invention. No lone genius stood up one night and solved the problem. Instead, the breakthrough came through relentless experimentation. One shell failed, another cracked less. A third penetrated. A temperature was adjusted. An alloy composition was modified. A nose shape was refined. A cap was redesigned. The answer emerged piece by piece. This is often how war-winning technology is created, not with one miracle, but with thousands of careful decisions. General Electric's role reflected the broader strength of American industry during the Second World War. Civilian companies became extensions of the war effort. Engineers who had once focused on power plants and medical equipment applied their knowledge to armor, ballistics, and production. Their work was technical, quiet, and mostly invisible, but its effects were unmistakable. A Sherman crew in France may never have heard the names of the engineers in Schenectady. They did not know who studied grain boundaries under microscopes or who reviewed high-speed film late into the night. What they knew was simpler. When they fired, they needed the shell to work. And increasingly, it did. The story also reveals something profound about armored warfare. Tank battles are often remembered for dramatic duels between steel giants. Panthers, Tigers, Shermans, and Pershings dominate the imagination. But the true contest began much earlier. It began in foundries, laboratories, and proving grounds. The outcome of a battle could depend on microscopic structures inside a piece of steel. A tiny crack, a slightly incorrect temper, a cap measured in millimeters. These details decided whether a projectile penetrated or shattered. The engineers understood this better than anyone. They knew that steel was not just steel. Its internal structure determined everything. Under the microscope, metal looked like a landscape of grains and boundaries. Under extreme stress, those structures either resisted fracture or failed catastrophically. The challenge was to create a projectile hard enough to bite into armor and tough enough to survive the shock. That balance was the secret, and once the secret was understood, German armor no longer seemed invincible. This did not mean every Panther could be destroyed easily. The Panther remained one of the most formidable tanks of the war. Its sloped frontal armor and excellent gun commanded respect until the final days of the conflict. But the aura of invulnerability was broken. American crews learned where to aim and gained ammunition that performed more reliably. Science reduced uncertainty. That reduction in uncertainty saved lives. The broader lesson extended beyond tank warfare. The Second World War was a struggle of production, logistics, and engineering as much as a clash of armies. Victories were shaped by machine tools, metallurgy, chemistry, and quality control. The nations that could solve complex technical problems quickly held a powerful advantage. General Electric was one part of that vast system. Its engineers did not storm beaches or command divisions, yet they helped provide the tools that allowed soldiers to survive and advance. Their battlefield was the proving ground. Their enemy was ignorance. Their weapon was understanding. Imagine one of those test days in Schenectady in the winter of 1943. Snow lies beyond the range. Engineers wait in thick coats behind reinforced concrete. Instruments are ready. Cameras are loaded. The projectile sits in the breech. A signal is given. The gun fires. The shock wave echoes across the frozen field. For a moment, no one speaks. Then they step forward to inspect the target. Did the shell crack? Did it ricochet? Did it penetrate? The answer will shape the next design, the next production run, and perhaps the next battle in Europe. This process repeats again and again. Hundreds of tests, thousands of observations, a mountain of data. Slowly, the mystery yields. The secret is not hidden in dramatic explosions. It is hidden in patience. By May 1945, Nazi Germany had surrendered. Burned-out tanks littered roads from Normandy to Berlin. Many factors brought the war in Europe to its end. Allied manpower, Soviet offensives, air superiority, logistics, and overwhelming industrial capacity. Among those factors was a quieter victory, the ability to understand how a shell met armor and how to make that shell survive the impact. It is easy to overlook such achievements because they happen far from the front. There are no famous battlefield photographs of engineers examining fractured steel under laboratory lights. No cheering crowds greeted improved heat treatment curves. No medals were pinned on a ballistic cap. Yet these innovations mattered enormously. Every time an American armor-piercing shell struck a German tank and stayed intact long enough to penetrate, the work of those engineers was present in that moment. In less than 1,000th of a second, years of research were put to the test, and when the armor gave way, so did the myth that Panzer steel could not be beaten. That is how General Electric engineers helped crack one of the most important secrets of armored warfare. They learned that victory over steel required understanding steel. They proved that a shell did not need to be merely harder. It needed to be smarter. And from the frozen proving grounds of New York to the battlefields of France, Belgium, and Germany, that knowledge traveled with every round loaded into an American gun. The tank crews at the front saw only the flash, felt the recoil, and watched the result. But behind that single shot stood years of science, thousands of failed tests, countless adjustments, and a group of engineers who turned broken steel into battlefield advantage. In the end, some of the most decisive blows against Germany's feared Panzer forces were not struck first in Normandy or the Ardennes. They were struck in the laboratory the instant a shattered shell revealed its secret to the men who refused to stop until they understood why.
If you want more content like this, subscribe now and comment below.